Hi there, welcome to VLMD Rounds, a podcast on medical science and tools to optimize your health. I'm Dr. Vivian Lowe. Today's episode is on the Renin-Angiotensin-Aldosterone System, or RAAS, RAAS, all in caps. And I'll be real honest, I'm going to be winging it more than usual. I sometimes wing it, but I think this time I will wing it a lot more than usual. And that's because I partied this week and took some extra dance classes and then hung out with my fellow dance groupie friends after class, and it was a blast, but I didn't get a lot of work done. And then I realized, oops, time to film another episode. But I think it was well worth it because my brain was tired. My brain's been tired the last few weeks. So, I'm glad I took those classes. I'm glad I took a break. And let's see how I do winging it. All right. The topic, RAAS. I have a little bit of history with this topic, and I'll fill you in as we get into the episode. Let's go. So, as I said, this Renin-Angiotensin-Aldosterone System. First, I'll start with how I learned about it, which is still how every med student is learning about it, which is still how the entire medical world seems to be thinking about it, really, even now, right? And this is sort of the classical RAAS system. And the way it goes is this. So generally, we think of RAAS as a system that is used to preserve blood volume in your body. So for example, if you were to cut yourself and to bleed out, or you were, unfortunate enough to be in an accident and you were bleeding out, that's an emergency situation for your body. And so we're going to activate your RAAS system to help you preserve your blood volume, okay, buy you some time until the ambulance gets there. So the idea with this is this is how it's taught. This is generally how it's taught. Your liver makes a protein called angiotensinogen, ANGIOTENSINOGEN, angiotensinogen. And it's floating around in the bloodstream, and in the event that you have a bad cut or a bad accident and you're bleeding out, then we have these cells in the kidney, the juxtaglomerular cells in a part of the kidney, and they can detect that you're losing some blood volume. And as a result, they're going to produce an enzyme called renin, R-E-N-I-N. And there are some dogmatic people who will insist that it's pronounced renin, R-E-N-I-N, from renal tissue. Quite. So renin is produced by these cells in the kidney, right? And what the renin does is it converts that angiotensinogen molecule to something called angiotensin 1. There's going to be a lot of numbers here. So here's angiotensin 1. And, it's going to get in your bloodstream and float around. And then when it gets to your lungs, it so happens that you have a lot of an enzyme called angiotensin converting enzyme in your lungs. ACE, A-C-E, all in caps. Okay, so ACE will now convert angiotensin 1 and make it angiotensin 2. And this is the bioactive component, really, of the RAAS system. So angiotensin 2 is a potent vasoconstrictor. So we're going to vasoconstrict and try to conserve some blood so you're not like just bleeding out like an open tap. right? And the other thing it will do is it's kind of a prothrombotic substance as well. So it increases coagulability in your blood so that you don't bleed out as easily, right? You're more prone to clotting a little bit, so that might limit the bleeding. So we have this angiotensin 2. In addition, we're going to stimulate the kidneys to reabsorb sodium. And that's because if we reabsorb sodium, then there's an osmotic effect and we draw back water from the urine, right, into the body because we want to keep the blood volume up. And the other thing that we'll do is stimulate the adrenal glands to produce a hormone called aldosterone. And aldosterone also increases the absorption or reabsorption of sodium from your urine. And also it will secrete or, cause the kidneys to excrete potassium in exchange for that sodium. Okay, so we're dumping out potassium and we're reabsorbing the sodium in exchange. Furthermore, we also stimulate the posterior pituitary to produce a hormone called antidiuretic hormone, ADH, otherwise known as vasopressin. And you've heard about vasopressin in other episodes, okay? So this antidiuretic hormone, just like its name suggests, is going to help you conserve water. You're not going to diurese or pee out as much water. Again, this is all to conserve or preserve your blood volume, right? So that's generally, I think, how the Renin-Angiotensin-Aldosterone System is taught, even today in med school. Okay, so dum-de-dum-de-dum, and that's how I learned it, and it was no big deal, and you just memorized it like you do everything in med school, right? Well, about 10 years ago, because I've always been interested in insulin resistance and metabolic syndrome, I came across an article. And in that article, it talked about how RAAS in the pancreas was responsible for insulin resistance. And I remember getting to that sentence and I just stopped and I went, what? And I reread that sentence 2, 3, 4, 60 times. I highlighted it and I thought, RAAS in the pancreas? I had never heard of this. And I was just blown away. And then I looked it up, and sure enough, there were lots of other articles. It wasn't a new thing, at least not in the scientific world. I hadn't seen any of it in the medical world. But in the scientific world, the basic science is, this wasn't a new thing. So I'm reading this and going, whoa, RAAS in the pancreas? And right after that, I had sort of a little gathering with other physicians, and I went to that, and I was so excited because I remember thinking to myself, oh wow, maybe other people have heard of this. How come I never knew about this? But I'm sure other people must have. It's such an important thing, right? So I went to this gathering, and the first thing I said was, hey, I read this article about the renin-angiotensin system in the pancreas. In the pancreas? Does anyone know about this? I never learned about this. Now, I didn't really attend a lot of classes in med school. I kind of skipped a lot of them, and I've talked about that in interviews and stuff like that. So I didn't go to class very often, so in my head I was like, this must have been something I missed, right? Oops. And I'm sure everyone knows about it. But turns out no one had heard of this. Not one, okay? So these are all other doctors, And I said, do you know about RAAS in the pancreas? Do you hear about this? And I'm holding up this article. And nobody had heard of it. And furthermore, they weren't that interested. They really didn't seem interested at all. And you know, at that moment, I just had a lot of self-doubt, I suppose, you know, because I was thinking, well, I thought this was important. Like, for some reason, I thought this was, but no one else seems to care. No one else seems to think this is important. I was like, you know, and I didn't miss it in med school because apparently they didn't teach this in med school. It wasn't like, you know, it was because I had skipped too many classes. But yet I was like, wow, this blows my mind. And no one else seems to care. And I was like, what's wrong with me? Why do I always think something's really amazing and no one else seems to care, right? But I was so taken by this that I really spent years after that pursuing this. I was very interested in RAAS because it turns out that we have components of RAAS, all the components of the Renin-Angiotensin-Aldosterone system in different tissues in our bodies. Okay, so if you're not from the medical world, this probably sounds like so big deal, right? But you know, all this time we'd only learned about the systemic RAAS. That was classically how we learned it, in your bloodstream. But now, for the first time, I was learning that it's in different tissues in your body. So it's in things like your kidney, your heart, your pancreas, as I said, and it's in the GI tract, in the eye, in the brain, you know? And so I was thinking, wow, this is really, really important because as I read, I realized that this system is probably one of the most inflammatory systems in our body, and when activated and out of control can cause a lot of damage to different tissues, right? So for example, when you have a lot of inflammation, we have components of RAAS that will stimulate fibrosis, right, in those tissues. And, you know, I thought that was a big thing because, you know, something like liver fibrosis, which essentially is cirrhosis when it gets to a certain extent, yeah, or fibrosis of the heart, so that you have heart failure, you have a heart that doesn't pump well now because it's all scarred up and fibrotic. These are important sort of pathophysiological, you know, occurrences in the body. And like I was thinking, well, what do I know? I'm just a clinician. But as a clinician, I think these things are pretty important, right? So I continued to read up on and pursue and learn as much as I could about tissue RAAS, okay? The Renin-Angiotensin-Aldosterone system in tissue. Because now we're not talking merely of a hormonal effect through the blood, but we're also talking about paracrine and autocrine effects. These are local effects. So that if the tissue is secreting all components of RAAS, then within that tissue, we're having effects. Those molecules are having effects on neighboring cells and on the cells that are producing those substances, right? And as I said, this can downstream lead to something as severe as fibrosis of the tissue. So, you know, for years, I kind of kept my little tissue RAAS secret to myself since no one else seemed to be interested in it at all. And then in 2020, we had the coronavirus, okay? So SARS-CoV-2. And I still remember the early days, just before the lockdown, there was a lot of confusion and people weren't sure what was going on. And, you know, my patients were worried. So I decided I'd do a little bit of research. And of course, I found out that SARS-CoV-2 is actually quite similar to SARS-CoV-1, you know, so which had been in Asia and, you know, didn't seem so important at the time because that was very far away and we didn't have to worry about it. But the good news about it was that they had done a lot of research on SARS-CoV-1, and since SARS-CoV-2 was quite similar to CoV-1, you know, had quite a lot to go with, right? So I was reading up on it, and of course, it involved, as everyone knows by now, the Renin-Angiotensin system. And that was right up my alley because I had spent years reading about this, and this was the thing I was trying to get everyone interested in, and nobody was interested. And when this virus came along, I had a lot of people call me and ask me, you know, well, why is it people with obesity and why is it people with hypertension seem to have this worse? And I was like, well, about the obesity thing, there's plenty of RAAS in adipose tissue. Okay, adipose tissue expresses the entire components of the RAAS system in huge amounts. Right? And, you know, anyway, I still remember right before the lockdown, it was maybe 2 days or the day even before the lockdown here in Massachusetts. It was in March, mid-March. I gathered all my patients together because we happened to have 3 classes going on that same day. So knowing that people were worried and this was at the top of people's minds, I said to Driss and Anna, let's forget the usual classes. I need to address this because all the patients are scared and worried. So I remember gathering all the classes, all the 3 classes, and putting everyone together. And there were at least 50 people, right? And I started to explain this to them. And I will say, this was 3 years ago. Every single thing I said that day still stands. I didn't have to change a thing 3 years later. And, you know, there were 50 people in the audience and Driss and Anna as well, listening in, as well as other staff at the time. So it was kind of a little bit of validation just because here was something I had been looking at for years that no one else seemed interested in. And I thought, wow, this is like very significant for the health of our patients, right? So anyway, you know, because of tissue RAAS, it was therefore no surprise when people were concerned about how the virus got into the body and how it seemed to affect the GI tract, RAAS tissue, right? The heart, RAAS tissue, kidney, RAAS tissue, lung, of course, RAAS tissue, right? And brain. Why was everyone surprised about the brain? Because no one thought about brain RAAS at the time, and I'm sad to say they probably still don't at this time. Okay, so let's just continue now, and what I want to do is focus in especially on the brain. One of the reasons I'm doing this episode is because friends and family have reached out. They've had long COVID, they have brain fog, or they have, you know, sort of neurological symptoms that they're worried about. And they asked me about it, and, you know, I thought I would at least kind of broach the subject, maybe to give us a little bit of an idea of what might be going on in the brain. Okay? So now with the brain, by the way, I just want to point out, this is one of the first textbooks on the Renin-Angiotensin system in the brain. that I'm holding up that I have here. It was published in 1982, I believe. And when I got the book, I was thinking, wow, it's like 40-something years old. And then I read the preface, and it said in the preface, the first publications on the presence of renin-angiotensinogen and angiotensin-like material in brain tissue appeared about 10 years ago. So 1970s, we've known about this. 50 years later, not in medical school, not in the general discourse in the medical world, right? Yeah, very disappointing, but oh well. So with the brain, let's talk about the brain now. The brain actually has exposure to RAAS from two different sort of pools, okay? The first one is the circulating pool, that classical RAAS system that I talked about that is, sort of in the bloodstream. That's the systemic RAAS, right? Now, we have a blood-brain barrier, as I have said in previous episodes, so that, it's really quite selective about what things can get into the brain, right? You have to have special transporters or be able somehow to penetrate the blood-brain barrier. So really, RAAS components can't get into the brain due to the blood-brain barrier, except for areas where the blood-brain barrier kind of falls apart, right? So these are the circumventricular organs. I talked about this in previous episodes as well. Okay, so in those areas, you do have some exposure of the brain in the medulla and the hypothalamus to circulating components of RAAS. All right, but other than that, the brain actually synthesizes all components of RAAS within itself. So it makes RAAS. And, there are complicated effects of this RAAS system on the central nervous system. So it's involved in sodium retention, in blood pressure regulation, but also many other functions. Okay, so as I said, there is de novo synthesis of RAAS components in the brain. So we make the angiotensinogen in the brain. Now, there's some debate about whether we make renin or not, okay? And if we make renin, there are some people who say we don't make a whole lot of it, but we make a lot of prorenin that has the capabilities of renin to convert angiotensinogen to other components of the RAAS system. So we may not have renin or a lot of renin, but the prorenin does the job in the brain. In addition, in the brain, we have renin B. Okay, now this is interesting because renin B is actually intracellular. It's not just in the brain, it's inside the brain cells, right? Intracellular regulation of brain RAAS. And then, of course, we have angiotensin 1 and angiotensin 2, like in the systemic RAAS system. And we have other components of RAAS as well that I didn't talk about. We have angiotensin 3, we have angiotensin 4, and we have angiotensin 1 to 7, and something called alamandine, which is from actually angiotensin 1 to 7. All right, so I told you a lot of numbers, but these are all different peptides of the renin-angiotensin system. And, they're just broken down by different enzymes, by prorenin, but there are other oligopeptidases that can break down these molecules and, give us all the different components of RAAS in brain tissue itself. And it appears that brain also actually makes aldosterone. Okay, so, and that's kind of scary, that your brain actually makes aldosterone as well. So as I said, you have all components of the renin-angiotensin-aldosterone system in the brain. Now, the main agents that, are active in the brain would be that angiotensin 2, which, as I said, is vasoconstrictive, right, in the bloodstream. We have that angiotensin 2, and then we have angiotensin 1 to 7, which has sort of opposite effects to angiotensin 2. We also have angiotensin 4. All right, so with angiotensin 2, angiotensin 2 can bind to certain receptors, and these are the angiotensin 2 type 1 receptors and angiotensin 2 type 2 receptors. Sorry about the numbers, but that's how they named them, okay? So angiotensin 2 binds to AT1 receptors and also AT2 receptors, but actually they bind a whole lot more to AT1. Okay, so there's some binding to AT2, they certainly can do that, but really primarily you're going to see more of the action through AT1 receptors, right? And then angiotensin 3 binds more to the AT2 receptors. And these are found in the cortex, in the hippocampus, in the basal ganglia in the brain. All right, furthermore, that AT1 receptor is broken down into subtypes. So we have AT1A, AT1B. And this is just based on different brain areas. So AT1A, for example, is found in brain regions that are involved in homeostatic processes, such as blood pressure regulation, electrolyte regulation, okay? So for homeostasis. Whereas AT1B receptors are seen in brain areas that are related to memory and higher brain functions, such as the cerebral cortex and the hippocampus. Okay, so again, just based on function, you have those receptors in different areas of the brain. Now, the AT2 receptor is it's found in areas involved in memory and learning. So things like the hippocampus, the cingulate cortex, the locus coeruleus, and so on. Okay, so that's where you find the AT2 receptors. These receptors, the AT1 receptors and the AT2 receptors, are seen in neurons and in all the glial cells. So in astrocytes, in microglia, in oligodendrocytes. And then we also have angiotensin 3, and that binds to AT4 receptor in angiotensin 4, that binds to the AT4 receptor in high concentrations. It can also bind to AT1 receptors, but really a lot more binding to the AT4 receptors, right? And just to be complete here, that AT4 receptor is actually identical to IRAP, which is insulin-regulated aminopeptidase, okay? So these are involved in things like endocytic trafficking and also receptor signaling in immune cells. And generally when you see IRAP, you're talking about muscle and adipose tissue, but you have AT4 in the brain, which essentially is IRAP in the brain. And the AT4 receptors in the brain are found in sensory and cognitive regions. So they have a potential role in learning and memory. And they're mostly on neurons, although there's some argument that they may also be on astrocytes. And then we have the angiotensin 1 to 7 molecule, and that binds to the MAS receptor, MAS, okay? So the MAS receptor, and there are some other receptors, we won't have to go into that, but the MAS receptor really is seen in areas associated with memory, cognition, smell, and so forth, okay? In addition, the angiotensin receptors can also be intracellular. Very interesting in the brain. They can be intracellular, so they can be found in the nucleus, in the mitochondria, plasma membrane, and any kind of vesicles, right, in the cells. And they function independently of the systemic RAAS. Okay, let's go back to the AT1 and AT2 receptors. The AT1 receptors are vasoconstrictive, right? They're involved in vasoconstriction, in cellular proliferation, cell growth, and they also produce a lot of superoxide, okay? So in the production of RAAS, or free radicals. The AT2 receptors are involved in vasodilation, and they have antioxidant and anti-inflammatory properties. So you can think of them as opposites. So AT1, vasoconstriction, AT2, vasodilation, and AT1 pro-inflammatory, and AT2 antioxidant, anti-inflammatory. The MAS receptor, by the way, is also anti-inflammatory, okay? Primarily anti-inflammatory, because the ligand for that is angiotensin 1 to 7. And that tends to have an opposite effect to angiotensin 2, which I told you is vasoconstrictive and also very inflammatory. Okay, so the different receptors in the brains, they, as I said earlier, they have some involvement with blood pressure regulation and homeostasis in the body, but they also have involvement in brain function, in cognition, and in memory. Right. So the thing that kind of really blew my mind and scared me a little bit when I first learned about brain RAAS a long, long time ago. This was a thing that stuck in my head and made me really worried about brain RAAS. You know, in the body, we're generally used to talking about negative feedback loops, right? So, you know, you have different processes, and then that those processes are controlled and maintained because they kind of regulate themselves. As we accumulate certain products, the accumulation of those products will shut off production of those products, for example. So a negative feedback loop. But brain RAAS, when I first read about this, and again, this was something I had to kind of reread several times when I first encountered it. We actually have a positive feed-forward mechanism seen with brain RAAS. So they did studies where they looked at a repetitive or chronic infusion of angiotensin 2 into the brain, into the ventricles of the brain directly, okay? So it's not systemic, they're putting it in the brain. And they noticed that with that instead of, usually when you have a lot of, you know, the ligand, then the receptor will downregulate. But what they saw was instead, when they had repetitive or chronic infusion of angiotensin 2, they had increased receptor expression in many of the brain areas. And rats that were exposed to angiotensin 2 at doses that didn't raise blood pressure, they were what we call non-pressor doses. So they didn't really do anything to the blood pressure, didn't raise the blood pressure. They were just exposed to this small dose of angiotensin 2 for a week, right? And when they were subsequently then given angiotensin 2, they really had an exaggerated blood pressure induced response to the angiotensin 2. So they had upregulated the receptors in the body, right, due to that primary exposure, and then on later exposure, they had now an exaggerated increase in blood pressure. And this was really a feed-forward effect, which when I read it, I was thinking, oh, that is very bad, right? And so we've known that sensitization to angiotensin 2 hypertension observed when animals were preconditioned with aldosterone, leptin, gestational hypertension, and a processed diet, right, led to this feed-forward loop. Okay, so what we're realizing now is that perhaps repetitive activation of brain RAAS in early childhood predisposes and sensitizes people to hypertension. Okay, that's, like I said, pretty scary because this is a positive feedback loop. And so, yeah, there's no way to control it and to dial it down, right? So, back to when we first heard about the coronavirus, actually, one of the things I said 3 years ago, I said, the thing I really worry about, yeah, you worry about the heart because that's not going to be good. Lungs, definitely, yeah. I said, you know what the thing is? The brain. I'm really worried about the brain because I was thinking about this feed-forward loop, right? And what might be happening to the brain. And of course, now we know that there are some significant impacts that have occurred with COVID in the brain, right? All right. So I mentioned earlier that we have a very pro-inflammatory system here with RAAS, right? Angiotensin 2 via the AT1 receptor activates ROS production, right? And this is mediated by NADPH oxidases. We call those NOx for short, NOx. And I like saying NOx is for noxious, okay? Because again, it is a primary generator of ROS in the body. Very, very inflammatory. And angiotensin 2 is a great inducer of NOx in your body, right? So that we have superoxide production by inflamed cells causing the death of dopaminergic neurons. And so we see actually cell death and neuronal death from this increase in reactive oxygen species by NOx activity. Okay. We also have decreased antioxidant enzymes like glutathione and superoxide dismutase. Okay, so we've known for a long time that, when you have strokes, when you have traumatic brain injuries, you have a seizure, an epileptic seizure, or you have, hypoglycemic induced damage to the brain, we see actually activation of NOx. Okay, and we have a lot of that damage occurring through this upregulation of NOx and the generation of free radicals in the brain, causing a lot of damage and cell death in the brain. And this happens when brain RAAS is activated. Okay? So when you have the system revved up, it may be hard to control because there may also be a feed-forward loop so that, it kind of just perpetuates this cycle of more oxidative stress. We generally know that when you activate NOx, right, then you're actually going to start this vicious cycle of more and more free radical production. And at the same time, you're depleting any of the antioxidants that you may be having. And as a result, we have this imbalance and more accumulation of damage in the brain. So there have been a lot of studies now that have looked at brain RAAS in certain neurodegenerative diseases. Certainly, they look at brain RAAS in conjunction with like traumatic brain injuries and the strokes and the seizures, like I mentioned before, but also some of the neurodegenerative diseases like Alzheimer's and Parkinson's, right? And they've noted activation of RAAS. So you have increased, for example, CSF RAAS components. And when they've also done autopsies of brain, they've seen upregulation of RAAS components in the brain in, let's say, the Alzheimer's patients and so forth. Now, there have been studies that have shown that the use of some medications, particularly the angiotensin receptor blockers. These are medications that are generally given to people to control their blood pressure. So they have names like valsartan and candesartan, telmisartan, losartan, right? So these are angiotensin receptor blockers. So they block the AT1 receptors, right? And that's how they function. And they've known that people who have been on these ARBs or angiotensin receptor blockers have a lower incidence of dementia, right? And there's been a lot of interest in kind of using this to look at therapeutic options for people with cognitive impairment or dementia symptoms, and different types of dementia. So they're looking at addressing various components of the RAAS system. So, some people have suggested that, maybe in people with higher risk for dementia that we should be putting them on ARBs, or potentially also putting them on some of the mineralocorticoid antagonists that will block aldosterone in different tissues. Okay, so I remember there was a recent live Q&A and someone asked me what some of my favorite medications were, and I've always said I have a very light touch with medications. I don't generally like putting people on medications, but if I put someone on a medication, I've thought a million times about it, and I at least am clear to myself what effect I'm trying to get in that patient, right? So I mentioned that some of my favorites are the ARBs and also the mineralocorticoid antagonists. And it's because, they can probably leverage the most anti-inflammatory effects in many cases in the body, okay? Because remember, the RAAS system is highly inflammatory and it promotes fibrosis. So it's a fibrotic system. So I think, addressing inflammation using ARBs and maybe aldosterone blockers might be useful. And certainly in the research arena, people have been thinking about that for a while, okay? So besides the brain, right, they've even looked at using some of these aldosterone blockers or ARBs in, let's say, liver fibrosis, or definitely in the cardiovascular system, right? These are drugs that are used in cardiology all the time, right? Because we want to prevent fibrosis of the heart and we want to prevent remodeling of the heart that way. So we know that there's an effect on the heart, and we also know there's an effect on the kidneys, right? So, now if we think about other RAAS tissue, we might be able to apply the use of these medications in the context of other RAAS tissue. In terms of the brain, like I said, people have associated that with decreased incidence of dementia. The ARBs can cross the blood-brain barrier. The ACE inhibitors, not as well, okay? And plus, the ACE inhibitors just block ACE enzymes, right? And there are many other enzymes in RAAS tissue that can form the different components of RAAS. Okay, so we're always used to thinking, again, we're taught it's that angiotensin converting enzyme that will, convert angiotensin 1 to angiotensin 2. But there are many other types of enzymes in different RAAS tissue that can actually do that, right? So it's not limited to ACE. So if you just give an ACE inhibitor, yes, you block ACE specifically, but you don't block the other enzymatic effects. Okay, so I just kind of gave an overview because I wanted people to understand that the RAAS system, I know we talk about it in a systemic way, but to me, what's more fascinating, more interesting, and at a clinical level, really more useful is to think of tissue RAAS, which I rarely hear anyone talking about. And a lot of times when we use medications that impact tissue RAAS, people are still thinking from the viewpoint of the systemic RAAS, okay? And they're not realizing that we may be impacting preferentially the tissue RAAS, which is what we want to get at, right? So let's do a quick wrap up for this week. We started by talking about the renin-angiotensin system, the classical way it's being taught. And I just gave you the whole rundown, and you could probably find it in any textbook, really, that whole system where, yeah, angiotensinogen is produced in the liver, and then we have renin made in the kidneys, and that will convert angiotensinogen to angiotensin 1. And then when we get to the lungs, we have plenty of angiotensin converting enzyme, or ACE, and that's going to convert angiotensin 1 to angiotensin 2, which is what raises your blood pressure by vasoconstriction through AT1 receptors, okay? And then I talk to you about how there's actually the entire components of the renin-angiotensin-aldosterone system present in different tissues in your body, like the heart, like the kidney, like the pancreas, right? Now, everybody's interested in insulin resistance and metabolic syndrome. But when I try to talk to them about the renin-angiotensin-aldosterone system in the pancreas, nobody's interested. And I'm like, that's got a huge thing to do with type 2 diabetes, apoptotic beta cells, right? Fibrotic pancreas, but seems like can't get anyone interested. But we do have RAAS in the liver. We have RAAS in the pancreas. We have it in the brain. And the scary part for me about the RAAS system in the brain is it has a homeostatic function, but it also impacts things like memory and cognition, for example, right? And so it has different functions in the brain. And at least with blood pressure regulation, we know it works through a feed-forward loop, which means we keep augmenting the response, right? There's no turn-off switch. So that's, to me, the scary part. And we can precondition people to having hypertension by just mere exposure, earlier on in life, right? So when we activate different components of RAAS in the brain, we set up generally a pro-inflammatory environment. Obviously, there are systems within RAAS that are anti-inflammatory and tries to balance off the pro-inflammatory effects. But if we are in conditions of poor metabolic health, for example, poor sleep, that's a big one, right? Then we're actually going to tip the balance over towards the inflammatory aspects. And now we have generation of reactive oxygen species through NADPH oxidase, otherwise known as NOx, okay? And it's one of the most inflammatory systems in the body with huge generation of reactive oxygen species. And it's a vicious cycle that keeps, kind of promoting more and more damage to brain cells, causing death of brain cells. And now brain RAAS has been implicated in obviously traumatic incidents in the brain and strokes and so forth, but also neurodegenerative diseases such as Alzheimer's, such as Parkinson's disease. And the thinking is that maybe we need better medications to kind of downregulate RAAS activation in different tissues in the body, to decrease the pro-inflammatory effects, to promote more anti-inflammatory and antioxidant effects, so different components of the RAAS. And Also to block the effects of aldosterone, which is highly fibrotic in different tissues. All right, I kind of winged it, but I think I deserved my break. So I'm just going to give myself that. All right, and hopefully it was interesting to you. I've always found tissue RAAS very interesting for so many years and never really get to talk about it. So I'm glad I was able to talk about it with you today. Right? If you have further questions, you want to hear about RAAS in pancreas, please, someone. I know that's just a wild hope, I guess. If you want to know more, if you have other questions, then write to me, and you can do that on the YouTube channel or through my website, vivianlohmd.com, VYVYANELOHMD.com. You could also maybe come to a live Q&A session, and my schedule is usually put on the website as well under events. So check out the next live Q&A, and maybe I'll see you there. But for now, signing out from VLMD Rounds, I'm Dr. Vivian Loh, and I sing the body electric. Bye for now.